morning, everyone. Welcome to another session of Network Seminar Series hosted by the Center for Network Intelligence at the Robert Boyd Center for Cyber Physical Systems, IIT. Today's talk is by Dr. Nikhil Karamchandani, and he will be speaking on online sampling algorithms for identifying the largest community. Dr. Nikhil Karamchandani received the MS and the PhD degrees from the Department of Electrical and Computer Engineering from the University of California at San Diego in 2007 and 2011, respectively. From 2011 to 2014, he was a postdoctoral scholar with the University of California at Los Angeles and the Information Theory and Application Center, University of California at San Diego. He is currently an associate professor with the Department of Electrical Engineering, IIT Bombay. His research interests include networks, information theory, and online learning. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. Finally, we request the online audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Dr. Nikhil directly. For the in-person audience, we have arranged coffee at the coffee machine in the adjacent building. Please help yourself to continue conversations over coffee after the talk. Over to you, Dr. Nikhil.
Thank you for the introduction and thank you for the invitation. And good afternoon, everyone. So, as was mentioned, I'm going to talk about some online sampling algorithms for identifying largest community. And this is joint work with my colleague Jay Krishnan Nair, and part of an ongoing work which has been led by students, both past and present. Okay, so let me just begin. Okay, all right. Okay, sorry again. So, okay, so let me give just a brief to begin with, just a brief outline of what we are interested in. So, we are given some, let's say, population of n individuals, and each of these individuals belongs to a certain community. Okay? So, this population is being partitioned into m communities, and our goal is that we want to sequentially sample from this community, from this population. And finally, we want to identify the largest community, or the community which has the largest membership. Okay? That is our overall goal. So I'm going to kind of talk about each of these in more detail. But broadly, this is kind of the setting. And so how does this sequential sampling, how is it going to happen? Okay? So what we are going to do is this population itself is going to be divided into some boxes. Okay? So think of each of these boxes as like a sampling domain. Okay? So there are B boxes. Each of these B boxes contains some part of the population. Okay? And these are what we are going to call boxes. And at any time, a learning agent can pick one of these boxes, okay, and sample from it. Now, what happens when an agent, let's say, chooses this middle box? So it will, when the agent chooses, let's say, this blue box, it's going to get or be able to observe a randomly chosen individual from that box. So what it will learn is both the community of that individual, so in this case denoted by orange, and the identity of that individual. So when I say the identity here, I mean, I have denoted this by Aadhaar, but you can even, we don't even need like a unique identifier like the Aadhaar or the social security number. As you will see, when we kind of design our algorithms, all that the algorithm needs to know is whether you have seen this individual before or not. Okay? So whether this individual is new or not is the kind of identity we are interested in. Okay? So in fact, what you can do is when you start sampling, you can just assign like a pseudo identity to any individual when you see it the first time. So let's say I sample from some box, I see some individual, I mark it brown. Next time I see the same individual, I'm going to mark it brown. If I see a new individual, I give them another sign. Okay, so all I need is some kind of a pseudo identity to be able to distinguish this. So that is kind of our sampling model. You choose a box, you observe a random individual from that box, and you get to know their community. Okay, so now the agent himself or herself has a fixed budget of some T samples. Okay? And its goal, as I said, is to estimate the largest community at the end of those T samples. And we want to design sampling strategies and decision rules which minimize the probability of error at the end of these T. The probability of error in being able to estimate the largest. So the error, so at the end, you are just choosing one of these n. So your output has to be between 1 to m being the number of communities. So at the end, you just pick. That is all here. This is the last. Yeah. Not telling the numbers, we're just telling the largest community. You see the network of connection. So here there is no graph or connection as such. This is just some population which has been divided into these boxes, and I can see where the box is and which those boxes are available to me. I am just going to the box and picking something from the box. So there is no underlying network here. No. So there is some underlying instance, but we haven't. So that is all part. That is all habit. Okay. So some applications to maybe motivate such a setting. So one, of course, like an election polling, right? You can think of these communities as being political parties. So everyone has some maybe preference. That is my community, and the boxes are constituencies here. So you can think of you go to some constituency and you randomly sample from that constituency, and if you kind of find the community which has the largest membership, that is telling you the party which has the popular vote, the party which has the largest following. Another application could be identifying the dominant virus strain. Temporary, I guess. So communities here would correspond to different strains of a virus. Okay. And the boxes would be different localities. So I go to different localities, I sample people, I see which strain of virus they might be infected from. And then if you find the community which has the largest membership, that is telling you the dominant strain. And the third one is a slightly different one, which is along the lines of a privacy aware recommendation. So think of like a recommendation engine, which is part of a system which has some content, let's say movies. Okay, and movies could belong to different genres like comedy, romance, action, so on, and there could even be subgenres. Within comedy, there is romantic comedy, dark comedy, slapstick comedy, and so on. So now, if I want to interact with this recommendation engine, one option for me is to tell the recommendation exactly which subgenre I want to watch something next. I want something from that one. But that would mean I'm revealing every time I'm telling the recommendation engine exactly what I'm looking for. I might want to hide some of this information, and one way to do that would be to give some course instructions. I want to watch something maybe from comedy, but you choose something at television. Okay, or I want to watch something from action or romance. So think of in this kind of a context, these boxes would correspond to these four types or four genres, and the exact communities would correspond to these subgenres. And depending on how much information you are willing to share with the recommendation engine, that would kind of trade off your privacy. Okay, so these are some of the applications which might lead to problems of these kinds. And some of you might recognize from the setting itself. Another sequential decision uh, uh, setting, which is very popular, which is the multi-arm bandit problem. And there are certainly connections to this problem, but as I'll indicate, there are also several key differences. So just for those who might not be familiar with the setting, the multi-arm bandit problem is again a sequential decision problem, and it's very popular in the literature. And the vanilla version of this problem is that you have some k arms, okay? And each of these arms is associated with some reward distribution. And when you pull an arm I, you get independent random reward generated from this distribution. Okay? And let's say associated with arm I is this expected reward, which is denoted here by mu1. Okay? So every time you pull an arm I, you get a reward generated from this distribution. And in this context, there is also this best arm identification problem or the pure exploration problem, where the goal is you kind of decide which arms to pull at what time and how many times each arm to pull, and finally what your goal is to identify the arm which has this highest expected reward. Okay. And again, the setting that might be most relevant to us, where the budget is fixed, is called the fixed budget setting, and there you have to again design the sequence of arm pulls and a decision rule at the end to identify the arm which has the highest expected. So clearly, one, you can kind of make the analogy with the type of problem we have. You might be tempted to think of, let's say, community I as arm I, right? And then maybe somehow map the size of the community to the reward associated with this arm. That might be one way to kind of model the problem as a multi-arm bandit. However, while we are going to in fact use some of these relationships and use some of this analogy, this problem by itself is not an MAB problem, at least not in this traditional way. There are kind of two key differences. The first one is, in our setting, you only have partial control of which arm you get to pull. So if I think of, let's say, each arm as being like a community, right? So if I go ahead and pull this box, I cannot go and pull, let's say, a sample from community I. My control is only over the box that I pull. I don't have full control over which arm to pull. The other hand, in an MAB problem, you can decide, I want to pull from arm 1, I want to now pull from arm 2, and so on. Here, that is not quite possible. You have partial control. You cannot use the box system for so then the question would be about how do you model? So if your goal was to identify the box with the largest size, then that would work. But here you have to also map the kind of the goal with the definition of your arm. So the goal is in terms of the communities, not in terms of the. And the other one, the other difference. So one is, of course, as I said, this partial control over which arm you pull, and the second one is that the observations from an arm are not IID. So if I think of this, as I said, you are getting this sequence of observations, and you are seeing whether you have, whether at any time you are seeing a new individual or an individual which you have seen before. The sequence is not IID. Right? The probability of seeing a new individual depends on how many individuals or how many distinct individuals you have seen before from this person. So in some sense, this is also, at least from, that is one difference from the vanilla maybe. Okay, so in terms of this problem, we are now going to kind of start with like some special setups and then build up towards the most general problem. Yeah. No, we don't know the size of each box. Yeah, I'll when I come to the end of towards the end of the talk, I'll maybe say what happens if you also know the size of a box. Then you can use that information to in fact get better performance. So I'll discuss that, but right now. Okay, so let's we'll start, as I said, with some special cases and then build up towards the general. Okay, so the first one will be okay, so again, the algorithms will not use the population size. If you know the population size, then you can maybe in some seconds do. Yeah. So as I said, I mean, right now we'll not assume that we know the population size, the overall population. Okay, so the first setup we are going to talk about is the mixed community setting, where you just have a single box. Okay, all the entire population is in this one box. So there is, in some sense, no sampling decision to be made at each time. Right, there is only one box. You just have to sample from that box, and all the T samples have to come from this box. So no sampling decision to be made. So you have no sampling control. The only thing that you have to do is at the end you have to make a decision based on whatever you have got. Yeah. You view that as a given possibility. That's going to determine the probability of error. So that will depend on the configuration. If there's some configuration dependence that will come in your answer. Yeah. So the probability error would depend on the underlying sampling and timing, etc. Okay, so yeah, so this is going to be the first setting where there is no sampling control. You just have a decision to be made at the end.
There was on that question. Okay. Do we assume anything on how the population is partitioned among the boxes?
Yeah. So that was the question that Rajesh was also asking before. We will consider that as the underlying instance. There is no assumption a priori. The instance will be determined by what is the kind of the size of each community, and our probability of error will also depend on that. So it will be an instance dependent. So we'll see that shortly, and I hope that for what? So for example, in the mixed community setting, anyways there is a single box, and as I build towards other settings, you will see that it's everything is part of the instance itself. So I'll define the communities and which community goes in which box. All of that is part of the underlying instance, and the probability of error will depend on this. Okay, so this is one setting. The other setting is like the other extreme. Okay, so in the first setting, in the mixed community setting, all the communities, all the individuals were in a single box. Here, this is like the other end, which is every community belongs to a separate box. So in each box, there is a unique community, and each community is a box in itself. Okay, so here you have kind of full sampling control if you want at each time. You can decide which community to sample from at every step. Right, and you will get a sample. Yeah. So in this talk, I'm going to talk about the fixed budget setting, where the number of samples is fixed. I'm targeting the minimum probability. I'm going to discuss the fixed confidence variant also, but yeah, we'll stick to this.
Can you unmute yourself and ask the question, please?
Yeah, hi. Nikhil Karamchandani here. I thought the other extreme would be where each node is a box. So there are as many boxes as the number of nodes.
Just 1 minute. We are not able to hear your question.
Hello, am I audible?
Or can you please type it up?
Yeah, sure, I'll do that.
Okay, all right. Okay. So yeah, so these are like two extremes, and then we'll study one setting in between, which is this, which we call the community disjoint box setting. Okay, so here now every box has multiple communities, okay, in it, but all the individuals belonging to a community lie in a single box. Okay? So for example, this box has two communities, blue and orange. This box has just a single community, yellow. Okay, but all the individuals of a given community are all present in one image. Okay? So this is like some, let's say, partial sampling control. Something I have some partial control over which community I can sample from, but not fully. Okay? And some of the algorithms that we design here are also going to tell us or give us insights into what kind of algorithms might work in the most general setting where communities are partitioned across boxes. So
So the
yeah, we'll go in.
Question is,
Yeah.
what if there are as many boxes as the number of nodes, each box having exactly one node?
So as I said, yeah, right now we are going to talk about these three settings. So in this particular setting, the disjoint box setting, you have each all the individuals belonging to one community in a single box. There might be multiple communities in the box, right? But all the individuals belonging to a community are in one box. That's the kind of. I mean, you can go to more general settings, but the talk, I'm going to mainly focus on these three at the granularity of these. Again, so one difference here is about what reward so that is not something that is IID there, right? So if you've seen certain number of individuals till now, distinct individuals till now, the probability of seeing a new individual depends on how many you've seen before. So if you want to map your reward in that way, it's not IID reward. So it's different from the standard MAB problem, although there have been MAB works which have studied Markovian reward as well. Ours is our setting is slightly different from those in terms of the exact structure of the Markovian reward. But I mean, yeah, you will see we do look or we do propose schemes which are very similar to what you would do in an MAB. Yeah.
The typical result is have the algorithm is aware of each set of situations and can adapt its sampling based on the knowledge. I'm looking at a separated community that is sample accordingly.
That's correct. Yeah, yeah.
It's the prior information.
Yeah, that is.
The population size is very huge. It's non-IID point.
So you mean that you just keep seeing new individuals, so on. So yeah, that would again be part of let's say the error probability that you will see. So if you are just seeing new individuals from, let's say, two different communities continuously, then in some sense that is also you won't be able to decide which among these is actually the largest, right? You are just seeing new individuals all the time. So then that also makes the decision harder at the end. You have so if you've seen, let's say, 10 individuals in 10 samples which are all unique here and 10 individuals in 10 samples all unique here, you have no way to kind of decide which amongst them is the largest one. So you will just need more samples. Okay, so let's begin with this mixed community setting where you have all the n individuals in one box. These individuals belong to different communities. You have an underlying instance, which I'll denote by D, and this D has the sizes of these each community. So Di denotes the size of community I. This is not known a priori to us, but this is the underlying instance. And without loss of generality, we are going to assume that these are arranged in decreasing order. So in fact, community 1 is the largest community. It is not something that is of course known to us a priori, but we just assume that these communities are labeled in this way. Okay, and so as I said before, there is no sampling control here. These individuals are sampled uniformly at random. Then, for example, first you might sample this individual. Then at the end of those 3 samples, you have to decide, come up with a decision rule and give an output saying which of these communities do you think is the largest, and that will give us probability of error. We want to minimize this probability of error after t sample. So give fixed value. Okay, so we'll start with a baseline scenario, which we call identity-less sampling. Okay, so in this model, what will happen is that you will still sample a random individual from the box, but you will only see the community information of this individual. Okay, so think of this as a private sampling, if you will. Okay. So I'm not able to see the identity of this individual, or whether this is a new individual, old individual. I'm not seeing that. All I get to see is which community does this individual belong. Okay, so if something like this happens, then let's say you sampled this individual first, you saw orange, then you sampled this individual, you saw blue, and so on. Right. So all your observations are just like a sequence of these colors, right? Which community are you observing at it? Blue, orange, orange, yellow, blue, orange, and so on. Okay. So if you think about it, this is just the observations are just IID samples from an underlying distribution, which is defined by the sizes of the various communities. Right? So the probability that you sample something from community I is proportional to the size of that community Di. Okay? So all you are seeing are samples from an underlying distribution which has this form, and so the task of identifying the largest community boils down to mode estimation from a sequence of IID. Okay, so this is, let's say, so our goal, we have T samples from an unknown distribution which has a certain EMF, and a natural mode estimate would be whichever community you've seen the most number of samples from, you output that as your estimate of the largest. Okay. So this can be easily analyzed, and we get a result of this kind, which gives an upper bound on the probability of error in terms of the number of samples and the underlying. Okay. And the proof of this is, I mean, easy enough that I can give you a quick sketch. So this is our underlying instance, and let's say you took T samples, and this XIT was the number of samples you saw from community I. Right? So the expected number of samples that you see from community I is T times Di by N. So you do expect, at least in expectation, you would have the largest number of samples from the largest community. And so our mode estimate is just the xi, the I, which corresponds to the largest value of number of samples. So the probability of error corresponds to the event that there is some other community from which you see more samples than the largest community, which was community. So this is just this event. You use union bound to upper bound it. Now you have these individual events. So this is the probability that the number of samples from the ith community is larger than the number of samples you observe from the first community, which is the last. So if you think a little bit, you can write this as a sum going from 1 to t, sum of t terms, each t IID terms, right? And those terms correspond to, will take the value 1 if you have seen a sample from community 1. It will take -1 if you have seen a sample from community 1. And it will be 0 if you have seen a sample from neither 1 nor I. So you can write that as a sample of IID terms and use basic Chernoff bound, and answer immediately kind of pops out in terms of this exponential bound, which is exactly. And so here the ith term will depend on the size of the ith community. We'll upper bound that by replacing that by d2, because that is the second largest. This gives us, so each of these individual terms here is bounded by this quantity, which is how you get the m-1 on the outside. Yeah. So right now we are in a identity-less setting where every time you sample, you just get to see the community of that individual, right? So if there are, let's say, Di individuals in a population of size n, no, it is with replacement. So everything is with replacement here. There is no without replacement. You're not removing that individual. If you remove that individual, then you will never see that individual again. So anyways, everything is with
That's exponent.
yeah,
The pre-constant also, because Karnaugh theorem,
yeah,
you're looking for
exactly.
another measure which is maximum not one.
Correct. Yeah. You can certainly title this result further. So our interest here is going to be mainly in the exponent, but you could tighten it further.
So my question was whether is it the tightest coming from Karnaugh theorem and the infimum coming from all the measures such that an alternate is better than one in terms of its empirical measure.
So in terms of the rate exponent, this is optimal. The three
somehow-
constants might be something that gives you
Somehow I feel the other these two are highly related. Maybe this is a bound because perhaps D2 and D3 if they are very close to each other, but let's say D3 is poorer than D2. Somehow I feel that that may have an impact on the exponent, which means that making this just a function of D1 to D2 may not be the tightest of the exponent. Might be a good bound.
So because you're interested in kind of, let's say, the largest community, right? So even this also happens in the, let's say, even in the MAB setup, right? The
most likely might be that the second one, is the first.
yeah. So that is kind of the bottleneck even. That is the decision that is the hardest to. Yeah, and so it turns out that in this setting, this rate exponent is in fact optimal, and yeah, this can be shown using a variety of methods. This is, you can think of it like application. Okay, so this is an instance dependent bound that we get in the identity less setting, where we are only using the community information. We are not using the actual identity information. So let's now go back to our identity based sampling strategy. Now I can see, right, whether I'm seeing a new individual or is this an individual that I've seen before. Right? And now again, the natural kind of estimator you would think of is you output the community from which you have seen the maximum number of distinct individuals. Okay? And one can again analyze this algorithm, and you can get an upper bound of this form, and this here is the rate exponent. So I'll just give a quick sketch maybe of the proof. So let's not, because we're now able to see this identity information. So let's say SIT is the number of distinct samples that you've seen from community I during these P samples. Okay. Now, if you think about it, so the largest community, it has, let's say, S1T distinct individuals that you've seen from. If that number is larger than the size of all the other communities, then you certainly won't have an error, right? From those communities, you cannot have a number of distinct individuals which is larger than their size. Okay, so if you have observed a number of distinct individuals from first community or the largest community which is larger than the size of the second largest one, which is D2 plus 1, then you certainly won't have an error. So this gives us a way to kind of upper bound the error. So the error event is you just look at the largest community and you ask what is the probability that a large enough subset of this largest community, particular D1 minus D2 individuals, are never sampled in these P of the list. Okay. So the probability of error just becomes the probability that S1T is less than equal to D2. And that is, as I said, that probability is upper bounded by the fact that there is a subset of D2 individuals in the largest, sorry, D1 minus D2 individuals in the largest community, which are never sampled. And that's what this probability is calculating, and that's what gives you the rate. Okay, so now I just want to make one remark here. There are also other ways of, this is one way, this is like a coupon collector type way of upper bounding this probability of error. There are also other ways of getting alternate error bounds. So for example, we could use a similar strategy to what we did in the identity less case, which is we write this probability of error by union bound. We write it as the probability that the ith community sees larger number of distinct individuals than the first community, and then you try and analyze the individual probability. So now you can't directly use, I mean, this is no longer a sum of IID type individuals, you have to use some other inequalities. In particular, we use McDermott inequality, but it's not difficult. That will also give you an error bound. It just turns out that this bound gives you the optimal error rate asymptotically. Other bounds can be tighter for moderate, but that's just something I wanted to point out.
There is one question from online audience.
Yeah.
Is it difficult to compute expected value of SI of t analytically?
You can compute expected value of SIT analytically. That is not the problem. The concentration might be a little harder, and the concentration is where this use of McDermott comes. You can do that. That's also an alternate strategy. It turns out that this error bound gives us the optimal rate. This one, as I said, it doesn't give us the optimal rate, but it can be better numerically for certain moderate than the previous one.
The other case I can understand in classification and the lower bound. So here,
So again, so what you use here is you again relate the probability of error. So you consider this original instance, let's say, in which the first community is the largest. You create an alternate instance where a community other than community 1 is the largest. And then you relate the probability of error. So an algorithm doesn't know the underlying instance. It should be able to identify community 1 as your largest community in instance 1, and it should be able to identify, let's say, community 2 in the alternate instance, if that is the largest community. So you relate the probability of error to the divergence between these underlying distributions and analyze the log likelihood. So here, the only difference is you have that log likelihood now has to take into account this Markov evolution, not IID anymore. So you need to take care of that Markov evolution, and you have to come up with the right alternate instance. So that is kind of the, let's say, the art in it. Some sense. You just have to come up with the right alternate instance which gives you the optimal error bound.
here is alternative one can support.
Okay, so yeah, so we now have something, we know what is the error rate using identity-based sampling, and we know what is the error rate if you ignore the identity information, and we can compare those two bounds, and we find indeed that identity information can greatly improve your decay rate. So if you use this information of whether you are seeing new samples or not, that can give you a much higher decay rate under certain instances than the case if you completely ignore this, let's say, identity information, do it in a completely private way in some sense. That can lead to a lower probability of error. This tells us quantifiably what is the, let's say, the gain that you get by using identity information in this. Okay, so you can also see this using some, these are just some synthetic sets. So we have taken 5,000 individuals, we have divided them into 6 communities here. And you can see, so the orange line here corresponds to the identity-less sampling, and the blue line corresponds to the identity-based sampling. Okay, and here these instances mainly differ in the fact that here the top 2 communities are very close to each other. So it's a harder instance in some sense to be able to find the largest one. Here they are more well separated. So you see here that when the gap is much larger when you have harder instances. Here the performance is more similar, let's say, when the instance is equal. The bounds essentially tell us when can identity give you much larger rate of it.
Is there an interpretation in terms of, just go back to the answer, so there is a notion of D1 minus D2 by N. So that seems like the L1 distance, whereas here I see a Bhattacharya distance. And
yeah,
is there a connection?
So it depends. So yeah, I mean, the probability of error bound is, at least the way we have kind of used the bound, is in terms of the scale divergence between the underlying instance. So you're trying to find an alternate instance which is what let's say an alternate instance which is closest in terms of that divergence. So it might not be L1. Yeah, whatever that
It's
is.
not exactly L1 because you're only focusing on the top two in both the cases.
Yeah.
You're saying that optimal level.
Yeah.
I was just wondering if there is a connection.
So the distance that comes up is scale divergence. It might be related to, there might be some bounding there which relates it to vertical.
Because all the other ones also.
Yeah. Okay, so we'll now move to the separated. Yeah. The second one is also another instance that is stated. So this denotes the sizes of the different communities. So this is one instance. So 5,000 individuals divided in two different ways amongst the 6 communities. So yeah, correct. Mhm. So I will take an underlying instance. I start generating samples, and at the end of those samples, whatever decision rule my algorithm makes, it will make, and then I'll see whether it has given me the right largest community or not. So in particular, whether it outputs community 1 as the largest or. And every time that happens, I count that as an error. Then if you do this, let's say over 1,000 times, then that gives you like an empirical probability effect. That is what we are plotting. Okay, so I'll now move on to the separated community setting where now each community is a separate box. You again have the same underlying instance, and we're going to assume that box, let's say D1 is larger than D2 is larger than Dn. So now you have full sampling control. You choose a particular box, and then you sample from that box. You get an individual from that particular community example. Okay? So every time you're deciding which community to sample from, and again we have the same goal of estimating the largest. Okay? So here we do use schemes which are popular in the MAB literature. So one class of schemes which are popular for this fixed budget setting is the successive elimination style scheme. Okay? So what you do broadly is you have B boxes, right? Or B is equal to N here. So whatever your number of boxes is, you partition your total sample budget into B minus 1 phases. Okay? And then within each phase, you uniformly distribute whatever the phase budget is amongst all the surviving boxes. At the end of each phase, so you maintain a score for each box or each community throughout, and at the end of each phase, you eliminate the worst box. Okay? So how do you score communities is something that you can change, and that will lead to different, let's say, variants of the same idea. But all you're doing is you're maintaining a score for each community or each box at every time. And at the end of a phase, you eliminate the worst performing box. Okay, and you keep going like that. So at the end of these B minus 1 phases, you will have a single box which is remaining, and that is the one you choose in this setting as your largest community. So you score each community or each box. Okay? You keep a score depending on what you have observed. You keep a score for each of them. What exactly or how exactly do you score them is something I'm going to talk about. But you're maintaining a score for each box or each community, and you eliminate the worst box in terms of the score at the end of each phase. So every phase, you are removing one of these.
Previous case, I mean, actually the previous two cases, the algorithm is natural. In fact, you can think of them as maximum likelihood.
Yes.
Here, though, it seems like the design of the algorithm itself is somewhat complicated. We're thinking of eliminating the worst box.
Yeah.
It could be, I mean, one could come up with a different formulation. Is there an approach that one could take? You look at the worst, I mean, you look at the lower bound, and then you see the worst case event and sort of have that guide you towards an algorithm.
So you can do something like
or ML, for example.
so the ML estimator here, I mean, you can write it down, but it's very tough to analyze. It doesn't quite give you any, let's say, heuristics. At least I don't know of any heuristics that directly come from the ML bound, which are analyzable. So one can come up with a variety of algorithms here, but this is one class of algorithms which you can analyze and give an actual error bound on. And turns out it is also optimal in some settings. And so this is again very much along the lines of what is done in the fixed budget setting for multi-arm bandits as well. There are other classes of algorithms. So I mean, here again you can think of essentially the score telling you, kind of giving you a proxy for how likely is this community to be the largest one. So in
For
fact,
example, just to articulate the concern or the question I have, why not eliminate 2 at a time? So that's a variation on this, which is faster. So maybe all of these could be guided by the view of the lower bound, then that suggesting perhaps what is to be done.
could be. I haven't really thought of that kind of variant here, but all I would say is that the way you score these boxes would be guided by what you think is a good proxy for the size. So, in fact, the algorithm that we are going to look at is where you score a box according to the number of distinct individuals that you've seen from that box so far. So that's similar to what was done in mixed community setting as well, where that was what we were using as our proxy for how likely is this community to be the largest. But you can use other scores as well. So this gives you, let's say, a wide enough window to experiment with different kinds of algorithms. But yeah, the choice of how many you eliminate at one time is also probably.
You could put a model on that and a parameter and the conjugate prior for that. And then keep a posterior based on your observation.
Yeah,
That's also very natural.
that's also a natural. Yeah, yeah. Certainly.
There is one more question from the online audience. How should we partition the budget depending on population distribution?
So here we are. So, so the budget itself across the phases is. I mean, again, that is a design choice. We choose. We take a choice which is something that has also been used in the MAB literature to get a bound which is tight to the lower bound. It is guided by what the lower bound is. Okay? That's how you choose your let's say budget across the phases. Within a phase, you divide the budget uniformly amongst all surviving boxes. And the reason that helps is that if you do it this way, if you divide the budget uniformly across boxes in every phase, across surviving boxes in every phase, then at the end of any phase, all surviving boxes have seen the same number of samples. Okay? So that does help the analysis a lot. Okay? That is the reason for doing it uniformly within a phase. If you do it non-uniformly, it becomes a mess to analyze. It can perform better, as we'll see via simulations, but it's a mess too. Okay, yeah. So as I said, we can use different criteria for scoring these boxes. Okay, let me quickly go over this. So this is one particular way of scoring boxes. It's called the consecutive collisions successive rigid algorithm, and this is inspired from another work which was studying a similar problem, but in a community exploration center. And the idea there is you actually try and map this problem to a multi-arm bandit problem, okay? And try and kind of get around this non-IID nature. And the way they do it is, I'll just describe it. So the way you do that is when you pull, so every arm is associated with one community or one box here. And when I say that you pull arm I, you draw 2 samples from community, okay? Not one, you draw 2 samples. So let's say you chose this community or this box, you get 1 sample and then you get another. Okay. Now you say that the reward is 1 if there is no collision, meaning 2 different individuals were chosen. And you say that the reward is 0 otherwise. So here you have reward 1. If in both the samples the same individual was chosen, then you say reward 0. If you define it this way, then the expected reward has this form 1 minus 1 by di. This is just the probability that you choose a different individual than the first one in the second pool. Right? So you can see that this expected reward is the largest for the largest community. So this problem now is exactly like an MAB problem where you're trying to estimate the arm with the largest expected reward. So now you can directly use the MAB algorithm, a successive regex algorithm that is from the MAB list. And yeah, each pool is generating independent reward because you're just looking at two consecutive pulls and then you're forgetting everything else. Then you go to another two consecutive pulls, forget everything. So you can analyze kind of the probability of error of that algorithm, and it gives you something in terms of this hardness parameter. Okay? This bound is mainly in terms of this hardness parameter, which has a certain form. I'm going to go there. So that was one possibility. We can also do something for communities based on what we have been doing so far, which is what is the number of distinct individuals you have seen from this community till now. And then you eliminate at the end of a phase the community from which you have seen the least number of individuals. Okay. In the interest of time, I'll just quickly skip over this. You can bound this probability, and the main takeaway is kind of you get a much this hardness constant, which when it's lower means you are getting a better decay rate, can be much better than the collision based algorithm that I had. That is something that was proposed in this. And again, this decay rate is optimal up to a logarithmic factor, and the lower bound uses idea similar to how things are shown in the MAB. Again, something that we can verify via simulation. Okay, so quickly, so in this community disjoint setting now, so now we have multiple communities within the same box. Okay, we can no longer decide exactly which community to sample from. Okay, so again, we are going to use the same idea of successively eliminating boxes, but the score of a box, we will look at all the communities within a box and choose the maximum number of individuals you've seen from a particular community in the box as its score. Okay, so this, you look at box I, you go over all communities in box I, how many individuals have you seen from community 1 in box I, community 2 in box I, and so on. Choose the maximum one, and that is your score for the box. So again, this gives me how likely is this box to contain the largest community. Okay, that's how I'm scoring it. And the rest of the algorithm is similar to what we did before. And at the end, now you have a box at the end, right? There are many communities in that box, and you have to pick one of those communities now as the estimate. So you output within, now once the box has been decided, you output the community with the largest number of distinct samples from that particular, which has survived, the last survived. Okay, so this combines elements from both the mixed and the separated settings, right? The separated setting is helping us decide the box which contains the largest community, and the mixed setting is at the end. You have identified the box, there are multiple communities within the box. So this is like the mixed community setting. So to now decide amongst them which is the mixed. And again, the decay rate is, we find it to be optimal, but the result is, I would admittedly weaker. It works for some broad class of instances, but not all. And in particular, place where it fails is where many of the large communities are within a very large box. They're all in the same box. What happens then is that even, you have all the largest communities in the same box, the samples assigned to that box gets kind of divided amongst these. And so their score of that box might be small initially, and it might get eliminated in the very first few rounds. Okay? And so this kind of an algorithm struggles in that kind of a setting. Okay? That's where we don't have a tightness. We come up with some other rules. So these are rules which kind of try and let's say take care of this issue of box sizes, of varying box sizes. If the box sizes are very skewed, how do you deal with that? Right? So it involves the box. You can either involve the box size itself in the sampling rule, or you can decide to split the budget proportionally to the box. But I mean, these are only, I think, a couple of them are something that we've been able to analyze. These work very well in simulations. but several of them are hard to analyze, or at least we don't have an analytical handle. Okay, so should I conclude in 2 minutes? Okay. Yeah. Okay, so just these are some simulations we did with some real data sets. The first one here is a data set from Brazil, which has apartment listings from different communities and states. So this is one of those instances which is tough for us. Okay, you have one box which is very large and it has all the top 4 communities. So you see, this is kind of our the distinct samples algorithm. It performs terrible. It's going to finally kind of start decaying, but in moderate budgets, it performs poorly. Others which are based or which use box size perform much better. This one on the right is a more balanced instance where the two top box sizes are kind of similar and the top communities are separated. Here things are much cleaner. Okay, so I won't go into the general setting now. I will just say that things perform well, but hard to analyze. These are still things which are very much open. So I'll conclude. So we formalized an online kind of community mode estimation problem, okay, where we have a population which might be divided into different sampling domains, and our goal is to find the community which has the largest size or has the largest membership. We came up with some algorithms in different, we looked at some special settings, came up with some algorithms, and also have some information theoretic converses. There are lots of open questions and further directions. Just the setting itself, one can look at cases where you have noisy observations. You don't always get to see exactly which community you were observed from. There is some noise there, or alternate sampling models. There is also the fixed, so we looked at a fixed budget variant, which is you fix the number of samples and ask what the probability of error is. There is also a fixed confidence variant where you first decide what your target probability of error is, and then you keep going on and at some point decide to stop. I think one can look at the sample complexity. And thirdly, I mean, so the broad idea was to look at situations where you have incomplete sampling control. And I talked about this relationship with the MAB problem or the multi-arm banded problem. There also one can look at an incomplete control type of setting. So suppose you take these arms, you divide them into boxes again. You can't pull an arm when you want to, but you can maybe pull a box. And then one of those arms will be pulled according to some distribution, and given you will be told the result. So how does, even in the MAB setting, a problem of that kind? Okay, so yeah, with that I'll conclude. Some of this work is based on application which is in performance. Yeah. All right, thanks a lot.
The hypothesis that community 1, community 2, community M. Okay, those are the M hypotheses. Is the largest, is the most. And then, depending on the structure of the problem, you get your sample. And you're in a fixed sample situation. Okay, so the relative entropies will come into the picture, but there is a nearest alternative within the class.
Yeah.
And we can write down a min-max problem it appears for this hypothesis testing problem. When you write this min-max setting, then the one that attains this min-max is sort of the nearest alternative. Sure. And viewing the max, I mean, depending on whether you're looking at, let's say, these are on the exponent, e to the minus. So the max is what the strategist who is trying to sample is trying to achieve. So the maximizing strategy will then be the correct. Correct. So I think it is possible to put it in this framework of a min-max. And then for every problem, of course, the min-max will be attained at a different location.
Yeah, so I can see what you're saying, and I think so I have seen let's say strategies along these lines in the fixed confidence setting where this track and stop strategy does something similar. You try and write a lower bound on the sample complexity, and that gives you this min-max type of framework, and then whatever fractions are being told by that max is what you try and target. So I think something similar
Yeah, I think in both cases, you drag and stop, it will come. In one case, the relative entropy will come as is, but in the other case, the turn-off entropy will come in the optimization. So I think there might be a general way to address all of these problems in one go, and then of course the specifics of the problem will
result in
depend on
different kind of.
yeah. So maybe that's the general way to attack this class of problems.
So are there any other questions? If there are no more questions, let's end this session. Thank you, Dr. Nikhil, for an interesting talk. As discussed before, we would like to remind the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. Thank you and have a great day.
Where is the copy?
Copy.